So students, the final step is about the purification of extracted metal. That means whatever metal we have extracted from the ore, now we need to purify that because still it has some impurities with it. And for different metals, we use different techniques like zone refining, vapor phase refining and many more. So let's study them in more detail.
Refining of metals, that means the methods used for purification of a metal which has been extracted from its ore. And the first method is actually distillation. You must be aware of the term distillation. It involves simply boiling of anything. So what is done in this method is, let's say I have a container which contains metal along with impurities, and the melting point of metal is low as compared to that of impurity. So if I start heating, if I provide heat to the mixture, what will happen? That metal will melt and eventually it will evaporate, and the vapors are collected and condensed in a separate container, and in this way I get the pure metal while impurities remain behind in that container only, because the melting point of impurities is very high as compared to that of metal. So when we start heating the mixture, what happens? That metal gets evaporated and we separate that out while the impurities remain behind. So this is a method which is based on actually, and it involves the evaporation of impure metals, and this is used for those metals only which have low boiling point, because if the boiling point of metal is very high, it would be very difficult to melt that and evaporate that. So we generally use this method for those metals which have low boiling point like zinc and mercury. Another method is liquation. In this what we do, we take the mixture of metal and impurity in actually molten form, and then we flow it over a slopy surface. We know there is a mixture, liquid mixture, it contains both metal plus impurities in melted form. Okay, now we know the melting point of, if the melting point of metal is low as compared to impurity, although both are present in the liquid form, or maybe that in only metal is present in the liquid form at that temperature while impurities are present in the solid form attached in that mixture. So if we flow it, what happens? That low melting metal flows out fastly, which is collected, while the high melting impurities remain behind and they take longer time to come down. And this is way we can separate both metal and impurities. This is again based on the melting points of metal. The melting point of metal must be low as compared to impurity, or vice versa. Okay. So these were the two methods, physical methods basically used for refining of some metals, and they are not used so often actually. But the another one is electrolytic refining, which is very important. So as the name suggests, what we do, we use basically electrolytic cell for refining of some metals. And for this what we do, okay, let's set up the electrolytic cell. We have this, then we have a cathode, a metal cathode, an anode and a cathode, which is attached with battery. This is the positive terminal of battery. This is negative terminal. So similarly, this is positive. This is negative. This is here anode. This is cathode. Okay, and anode is made up of impure metal. Impure metal. While this is pure metal. Pure metal, and we have electrolyte, which is nothing but aqueous salt of that method. This is electrolyte, that metal. So what is the setup basically? That we have electrolytic cell in which both anode and cathode are made up of the same metal, let's say, but the difference is that anode is made up of impure metal, which is thick as it is appearing, while the cathode is made up of pure metal. For example, if I have to do the electrolysis or the refining of copper, then I'll take impure copper as anode, while a thin strip of pure copper as cathode. So what will happen as the process will take place, you will see that the thickness of impure metal will keep on decreasing while the thickness of pure metal will keep on increasing. Eventually the metal will come down from this side and will attach on this side. So again, what is the setup? We have an electrolytic cell in which anode is made up of impure metal, cathode is made up of pure metal, and electrolyte is obviously salt solution of that metal. That means if I have copper, then this is impure copper, this is pure copper, and this is copper sulfate. Okay, so what are the basically reactions taking place? That as the electricity is passed, this at anode metal, that is impure metal from this side, gets oxidized to release n number of electrons, and these n number of electrons come to the cathode and they are taken by the metals present in electrolyte to form metal, which gets deposited on this. So here there is a metal which loses electrons and go into the solution. Electrons are carried away through this wire to cathode. Electrons come from this side. Now there are n positive ions present in the electrolyte. They take this electron and they get deposited on this in the form of metal. So this is basic the reaction. So if I have copper, what will happen? Okay, let's take the example of copper. This side I have impure copper which has some impurities attached with it. Let's say these dots represent impurity. Then what will happen at anode? The copper will convert into copper 2 positive, releasing 2 electrons, and the impurities remain behind and they will get deposit at this point at the bottom of the cell. These electrons will flow through external circuit and reach the cathode, where these 2 electrons would be taken by the 2 positive ions present in the electrolyte to make copper, which will get attached on the cathode. So thickness of cathode will keep on increasing while that of anode will keep on decreasing, and the impurity will get accumulated at the bottom in the form of anode mud. So this is how the electrolytic refining takes place. Next is zone refining, and it is based on the principle that impurities are more soluble in molten state of metal than the solid state. That means, okay, I'll tell you what happens. So what is actually that in this setup we take a rod of impure metal. Okay, the rod in the form of bar, which is impure, and then we take a circular heater, movable heater in this way. Let's say we have heater. Okay, so this is heater. So what happens that this region of the metal gets heated and it melts actually. So there is a melted region in this rod bar. So now what is the tendency actually? That impurities are more soluble in molten state of metal than in solid state. So what will happen, that all the impurities will get accumulated in this area, because they have more solubility in molten area as compared to solid area. Now as this is moved, as we move this heater on the bar, heater moves up to, let's say, this side. So this molten range or molten area also moves along with the heater, the movable heater. So let's say after some time it reaches at this point. So what happens? We are moving heater, along with the molten zone is also moving, and as the as the tendency of impurities is higher to be in molten form, they also move along with the molten zone. So as the heater is moved with the time, the molten zone also moves, and also the impurity move along with the molten zone and this heater. And at the time when we reach at another end of the bar, all the impurities are present in this molten zone. So what we do, we can easily cut it out. So all the impurities of the solid of the metal are accumulated in this area, and we cut this side. So we have now a sample which is highly pure. So in this process, a circular heater is fixed at one end of the rod of the impure metal. As the heater moves, the molten zone of the rod also moves along with it. As a result, pure metal crystallizes out and melts out the melt, and the impurities pass to the adjacent molten zone. That means again the same thing. Heater is moving, so molten zone is also moving along with this, and impurities are also moving with the molten zone because they have more tendency to remain in molten zone as compared to solid zone. This process is repeated several times, which leads to the segregation or accumulation of the impurities at one end of the rod. Then the end with impurities is cut off. So we have a sample which is smaller in size, but it is highly pure. So this is how zone refining works, and basically it is used for purification of semiconductors. Now vapor phase refining. This is the process. Okay, let me explain you first in simple way. Then what is vapor phase refining? Okay, in this what we do, let's say I have a metal, I say it indicated by M, which has impurity. Okay, so this metal is not volatile. Okay, what is volatile? Volatile is the term which is used for those substances which can easily converted into vapor. So this metal is not volatile, so impurities are attached with it. Okay, now if I do some chemical changes or some chemical reaction, carry out some chemical reaction with this metal and impurity compound, this metal will get converted into some compound which is now, if volatile, again it has impurities with it. Okay, so I have carried out some chemical reaction to convert this metal into metal compound. Now the metal compound which is formed now is volatile in nature. So if I heat it, it will eventually get converted into vapors. Okay, leaving behind the impurity. I again collect this vapor and then decompose it to get my metal back while the impurities are remain behind. So this type of actually refining is known as vapor phase refining, in which impure metal is converted into its volatile compound, which is decomposed to obtain the pure metal. And for this process, the metal should have volatile compounds with its available reagent. The volatile compounds should easily decompose so that metal can easily be recovered, and it is basically used for nickel, zirconium and titanium for the refining of these metals. Okay, so next is Mond's process. Okay, so as you can see from here, what we do in Mond's process, it is used for refining of nickel. You can see here, nickel contains some impurities. Then it is reacted with carbon monoxide at 330 to 350 Kelvin temperature, and we get a compound nickel CO4. Also it has some impurities attached with this, these impurities. Okay, and this is actually a volatile compound, or volatile, we can say a complex molecule, volatile complex. Now when it is further heated with at 450 or 470 Kelvin temperature, this gets decomposed. First it goes into the vapor phase, and then it gets decomposed into nickel and 4 carbon monoxide molecules, while the impurities remain behind. Okay. So these dotted actually indicate impurity here. So this is method Mons process used for refining of nickel, in which first impure nickel is reacted with carbon monoxide to form a volatile complex, which is converted into vapor and then decomposed on further heating to get nickel back, while the impurities remain behind in solid form. Next is Van Arkel method. This is used for getting ultra pure metals, and the principle involves is to convert the metal into volatile unstable compound and to subsequently decompose it to give a pure metal, just like any other vapor phase refining. And this is basically used for titanium and zirconium, etc. And this what is done, let's have a look at this titanium. We first take titanium solid with impurity, not pure titanium. This is first reacted with iodine gas at 523 Kelvin, and we get titanium tetraiodide, which is gas. Then this and impurities remain behind in solid form. Then this titanium tetraiodide is further heated up to 1700 Kelvin to get pure titanium back and 2 molecules of iodine. This was impure along with impurities. This is pure titanium and the impurities remain behind. So this is how Van Arkel method is for refining is carried out. Okay, next we have some solved problems. The first and very simple one actually, because the first question is high impurity copper is obtained by, obviously for copper we use electrolytic refining, we have discussed it. Next is, in electrolytic refining the impure metal is made up of, yes, it is made up of anode. What is done, let me remind you once again. We use impure metal here at anode, then we take pure metal at cathode. We have electrolyte, then we connect it to the battery. So what happens that at this side metal gets converted into metal, ion and electron, and these electrons are carried out by the external circuit up to cathode, and in cathode the N positive ion present in the electrolyte get these electrons to form metal, which gets decomposed on cathode. So thickness of impure anode keeps on decreasing while that of cathode keep on increasing, and the impurities are accumulated at the bottom in the form of anode mud. So B is the correct option. Impure metal is made anode and the pure one is made cathode.
So these were the methods used for refining of different metals, zone refining and vapor phase refining, and some other words also important. In next video we will basically focus on metallurgy of two important metals, aluminium and iron. So keep watching.